We are the Earth team, and our product is an autonomous hole digger. Team members are me, Audrey Adam, Lei Jin, Cole Morter, Austin Tang, Daniel Tang, and Chris Wang. Hole digging is a widely used aspect of farming. Some crops only require indentations in the soil to drop seeds into, others require deep holes. Things that require holes include vineyard, like vine transplants, or orchard tree transplants, as you can see below. And above is a tarp dust fence that goes around every field that has delicate crops on it, like berries, to keep the dust from passing cars from getting on the crops and hindering their growth. Holes are also widely used in the construction industry to build fences, as they are used in the farming industry to also build fences. So the problem with digging holes. The current method of digging holes involves small tractors, like the one pictured here, with an auger attachment on the end. There are many different attachments that you can include on a small tractor like this, but the auger attachment is useful for digging holes, obviously. Those are mostly used for tree transplanting and vineyard vine transplanting, and the post hole digger, also pictured, is typically used for drilling holes in the ground that are post size, so for posts, like the fence pictured in the last slide. The problem with this is that they have a human element involved. This costs the farm money because the speed with which you can dig a hole is limited by working hours of the humans, and they have to adjust and make mental calculations for where each hole is going to be. You also have to pay an employee to do this super repetitive, very mundane task, and their time could be better spent doing something else. So our solution to this problem is automating the hole digging process. This could reduce the number of employees required to accomplish a task. For example, the dust fence is 4 employees, 1 on a tractor, 3 putting up the fence, and they can dig 1,000 feet of fence, or install 1,000 feet of fence per day. So automating it would bump that down to 3 people per day and potentially increase the speed of fence construction. This would save money in payroll and would decrease the downtime between harvests, so maximizing crop turnover. We've reached out to both the agricultural and the construction industry, and they are both interested in a product like this, and there's no product on the market that currently meets these demands.
So this is a simple design overview of our project. As you can see, our machine is quite large. The dimensions are 14.5 feet long, 6.5 feet high, and roughly 7 feet wide. It's also very dense. Its internal components and all components weigh roughly 2 tons. For our project, we are digging, the minimum specifications for digging are a 12-inch diameter or 1 foot diameter hole with of 1 foot depth. And then some basic specs. Our whole project is based on hydraulics. We have a diesel engine that powers the hydraulic pump, and this pump powers and supplies the hydraulic needs of the whole project. The wheels that we have and their motors, their respective motors, allow for a maximum speed of about 18 miles per hour, and the rough estimated cost of all the supplies and all the labor is roughly $40,000. This is a simple animation of how our project works. The linear translator moves up and down, as you can see. It's a system of linkages that Austin will go over. But these are 2 different views of our project as as it moves from the top position to the lower position?
So our hole digging assembly would not be complete without the hole digger itself. So we started the assembly by choosing an auger and auger motor. We knew we wanted to design based on vineyard vine transplanting, which requires a 1 foot hole, a 1 foot depth of hole, and the holes are 6 feet apart. So we contacted the vendor, Premier Attachments, based in Fort Wayne, Indiana, who was working from home due to coronavirus, so it was a little bit difficult, but we told them our requirements and where we were located, and they suggested a standard duty double flighted auger in the gray on the bottom left. And the double flighted auger is a little bit stronger than the single flighted auger, and it is better for the hard California soil that we assume that our product would be digging into, seeing as we're based in Southern California. And he suggested a standard duty auger drive, the MD12, which is 2 steps above the standard auger drive that they sell, just a little bit stronger for the hard California soil. He also recommended this universal joint that you can see on the top left and the image on the right. This allows for rotation in the X and Y direction so that gravity can be used to straighten the auger to dig holes vertically into the ground instead of having to have a horizontal leveling mechanism attached to our vehicle. The Premier Attachments policy is to not give out their CAD models, so we had to design our own based on the drawings that they would give us.
You might have seen the linkage system in the animation slides earlier. And the reason why we needed such a complex linkage system was for 2 reasons. So the first one was that we wanted to make sure that the auger moves in a purely vertical direction. So if you look at these graphics on the right, you'll see that in most traditional auger systems, the auger will come down in an arcing motion because it has a very simple mechanism that brings the auger down. And as the auger digs the hole, the driver or the operator has to make corrections because the auger deviates from vertical as it digs the hole. And the operator makes these corrections by putting inputs into the wheel, into the drive wheels. And we wanted to make sure, since we didn't have an operator and we just had a control system, in order to simplify the control system, we wanted to isolate the wheels from having to be involved in the entire digging process. And that was one of the main reasons why we made this linkage that would ensure only vertical displacement of the auger. And the other reason was we wanted to take advantage of hydraulics, which are capable of producing high forces. And we wanted to translate a small displacement from a hydraulic piston into a larger vertical auger displacement. So as for inspiration for our linkage system, we looked back at our 162A project, mechanisms class. And for that project, we had to make a linear translating table that was based off of the Chebyshev linkage, which is shown on the right. As we can see here, point C, which is in the middle of the small link AB, its path is traced out in the green. And as you can see, in this bottom part of the path, point C moves in a relatively straight horizontal line. And so we took advantage of this by turning this on its side and making point C move vertically and attaching the auger essentially to that point to ensure that the auger moves vertically and doesn't have any sort of horizontal displacement. This is a figure of our final design of the linkage. As you can see, links 1, 2, 3, and 4 are the original Chebyshev linkage, and links 5 and 6 were used in our 162A project, but we repurposed these links for mounting the auger lower down on the linkage. And the reason we wanted this lower attachment point was to ensure that the hole would be able to dig, or the auger would be able to dig a deep enough hole. And another note is that 2 of these linkages were used in our hole digger. And the reason for this was, so 2 of the linkages were straddling either side of the auger. And we wanted to reduce the moment experienced by one of the individual linkages caused by the weight of the auger. And then the other reason was with 2 pistons, we could distribute the hydraulic load between 2 pistons instead of having it all go on 1 piston. And the way that we designed the links themselves in the linkage was that we used Newton-Raphson method, which we implemented through MATLAB. And after being able to determine all the lengths and orientations of each of these links, the other main factor we had to consider was our hydraulic piston, which provides the input force onto the input link 2 in order to lift the auger up back to its starting position. So some of the factors that we had to consider here were A, the maximum force that the piston has to exert so that we could size the piston accordingly. And also we had to consider where the piston mounts onto the ground link, link 1, and onto the input link, link 2. Now, these 2 factors are interconnected, as you'll see later in the slides. But for the maximum force that the piston has to exert, we quickly made a reasonable assumption that our maximum loading condition on the piston would occur when the linkage is at its bottom position, which is shown here on the right, or in other words, when the auger is at the bottom of the hole. So the reason for this is that from the top position going down to the bottom position, gravity is doing most of the work to bring all the components down into the hole. And the piston, therefore, doesn't have to do very much. But the moment we want to come out of the hole, the piston has to lift the weight of the linkage, the auger, hydraulic fluid, and whatever excess dirt might still be on the auger. And so we were able to conclude that that was the maximum loading condition for the piston, and therefore we did static force analysis in that configuration in order to determine the maximum force that the piston has to exert. Specifically, the way that we did this was that we used a MATLAB script which determined the mounting points on the input link and the ground link for the piston such that the force that the piston had to exert at the bottom configuration was minimized. So this is an overview of all of the variables that went into the MATLAB script. So on this figure on the right, you can see that the left graphic shows the linkage at the bottom position, and the graphic on the right shows the linkage at the top position, and our user inputted variables are shown in green. So these included theta min and theta max. These 2 variables define the angular input range of the input link. F out max, which is the estimated weight of everything that the piston has to lift out of the hole at the bottom configuration. And also distance A, which is the distance from the top joint to where the piston mounts onto the input link. Now the outputs, which were generated by MATLAB, are shown in red. So these included F in max, which is calculated from F out max, and that's what we use to size the piston. Distance B, which is the distance from the top joint to where the piston attaches to the ground link. LPR, which is the retracted piston length. LPE, the extended piston length. and also the range, which is how much vertical translation the auger is able to achieve. Now, to determine Fin max, we had this complex linkage system, and we decided to simplify it into a black box model. So in terms of what's going into the black box model, we had Fin from the piston, and that caused an output at where the auger attaches onto the linkage of F out. And after defining these inputs and outputs, we simply applied a conservation of energy such that the force times the displacement of the piston is equal to the force times displacement of the auger. And from there, we were able to solve for Fin max. So Fin max of the piston is equal to F out max times displacement of the auger over displacement of the piston. So as we talked about before, F out max is a user specified value, and we know the displacement of the auger from the Newton-Raphson method. So all that's left is to determine the displacement of the piston. Now, in order to do this, we used trigonometry, which is shown on the right in this figure. So we know theta, which is this green theta right here, from the Newton-Raphson method, and B is an output, but we're assuming that we know this. This is why the mounting points and the force analysis were kind of interconnected, because we had to sort of figure out the mounting points in order to figure out the force analysis, but the mounting points also relied on the force analysis. So they were very interconnected, and it was definitely a very iterative approach. But right now we're assuming that we have a B value. And from there, we were able to determine this angle alpha right here as the inverse tangent of 3 inches over B. So what that 3 inches is we made another assumption, or a constraint rather, that we would be mounting the hydraulic piston 3 inches to the left of the line that connects the joints on the ground link. And yeah, from there we were able to determine the small angle alpha, and therefore we were able to determine theta prime, which is just the difference between theta and alpha. And we were also able to determine B prime, which is the distance from the top joint to exactly where the piston mounts onto the ground link. And that was the square root of 3 inches squared plus B squared. And finally, using all of that information, we were able to use the law of cosines to determine the formula for the length of the piston, L prime. And that was just the square root of B prime squared plus A squared minus 2 times A times B prime times cosine of theta prime. And now that we know L prime, we could derive an expression for the displacement of the piston. And finally, because now we know F out max, the displacement of the auger, and the displacement of the piston, we can calculate F in max. So now knowing or having a methodology to calculate F in max, we can now worry about the mounting points. So the way that we optimized the mounting points was, so first of all, we specified the distance A from top joint to where the piston mounts onto the input link. And after that, we defined a range, which is shown here in the this green rectangle. And this range is all of the possible mounting points of the piston onto the ground link. These range from 100 millimeters from the top joint all the way to the bottom joint on the ground link. And after defining both of those inputs, we put them into the MATLAB script, and they spat out calculations for the ratio between the displacement of the piston and the displacement of the the auger. And this this approach was shown in a graph form on the right here. And in this bottom right plot, the y-axis is the displacement of the piston over the displacement of the auger. And the x-axis is the distance from the top joint to where the piston mounts on the ground link, or in other words, the variable b that we were talking about before. So we wanted to maximize the ratio of piston to auger displacement, because as that gets larger, that means that the mechanical advantage of the piston is larger, and it doesn't have to exert as large of a force as with other configurations. So on this graph, it looks like around 840 millimeters is where the maximum piston to auger displacement ratio occurs. And that's the one that we chose, but there is a caveat to that, which I will talk about right now. So that caveat is that maximum piston to auger displacement ratio configuration is actually impossible. And that's because after we calculated some of our other output variables, including the extended piston length and the retracted piston length, we concluded that it was impossible for this configuration to work, because the extended piston length was more than 2 times the retracted piston length. And that's just impossible because a piston can't extend from its retracted length longer than its full retracted length. So now that after we factored it in into the script, we actually found that 991 millimeters was the greatest mechanical advantage that we could achieve while having a possible configuration. And that's shown in the green dot here, and the red dot shows the actual max at 840 millimeters. But the mechanical advantage is still high compared to all of the rest of the B values that we could have chosen. Now that we have all of the piston characteristics from its maximum force that has to exert to where it mounts on the input link and the ground link, we can select a piston, which Chris will talk about in the next slide.
So from the hydraulic piston specifications that Austin was able to specify from his MATLAB code, we were able to find a distributor that makes custom designed pistons. Parker, this company makes pistons out of steel and ductile iron, and it allows you to select whatever specifications you want, with including custom bore, or you can specify the stroke that you want. So this specific piston that we customized, we made it with a bore of 1.5 inches, and it has a stroke of roughly 16 inches, and it will be able to support an operating pressure of 3,000 psi. In addition, on either end of the piston, there is mounts that we have selected. This is also a custom part. This end mount is fitted, press fitted into the piston itself, so it will be secured, and the end has a spherical bearing. This allows for rotation of the links that it connects to. There's also a spherical bearing on the end of the piston, so that rotation can happen on both sides. In our design, we also needed to create a joint that would help support the loads that the linkage members apply on each other, especially since this linkage has a lot of large forces applied to it. There is a need for a joint that will help support these loads as they are translated upon each other. This joint was made of a combination of off-the-shelf parts as well as parts that will be manufactured. The off-the-shelf parts include the bolt, the nut, and the bearings. The bolt is roughly 5/8 of an inch in diameter. and the nut is a custom nut that fits that, and it runs the length of both the members. Along this bolt on one side, it could be on either side, but along one side there are two bearings that are attached. These are the needle bearings that we have talked about, and these needle bearings are what's going to be bearing the load that is applied onto this whole joint. And the calculations have been done to prove that these bearings are sufficient, have a sufficient strength to support the maximum loads that we are expecting. The other parts are manufactured, and that includes a combination of different metal casings and housings, including press fits and slip fits. A slip fit is adapted between the joint and the screw. So the slip fit is the one that connects this joint and it prevents this bolt from slipping out. And the press fit is between the linkage and from joint to joint. So that includes the connections between these two sides on both members and between.
So in order to, actuate or have relative movement between the links, you need a joint, right? And so basically we did a beam bending analysis on it to figure out whether the radial bearing loads were sufficient, or rather whether the bearings could handle those radial loads. And then once we did that analysis, we figured out, oh no, these bearings aren't strong enough. So we replaced standard ball bearings with needle bearings, which have much more surface area to sustain those radial loads. And that raised our factor of safety from about 1 to about 3.76. And we spoke with Matt, Audrey's cousin, and he's an agricultural engineer. And he stated that the standard factor of safety for farm equipment was 4. And then we brought this to Dr. Rosen, presented it to Dr. Rosen. He said that in certain cases, it is acceptable to be a bit below your factor of safety, especially if, it's 3.76 isn't that far away from 4. And 4 is an arbitrary number anyway. So as long as you know that it's not going to break, then that's all that really matters.
So for our drive system, we chose to do a hydraulic drive system. For our motors, we chose the Mark 18 porcelain motors. I know that really doesn't mean anything specifically to you, but those were just the motors that we selected based on our specific power and torque specs that we needed. The motor housing was designed to regulate temperature while protecting from dust. And one of the main reasons that we chose, there's 2 main reasons that we chose a hydraulic drive system. One is for the use of skid steering. As you can see in the bottom left-hand corner here, you have a little skid steer going around. The skid steer is advantageous for our project because, as you guys know, our project is an autonomous vehicle, and it is much easier to control a skid steer like via coding. And also, skid steering allows for 0-point turning, as you can see in the picture down there. This 0-point turning is very important for our design because we're going to be doing a lot of straight lines and fences. And the thing about doing like continuous straight lines is they usually butt up to another line in a 90-degree. And if we had something with conventional style steering, it'd be very difficult to go from the one straight line and then either turn 90 degrees on a very short radius or do a 180 to the next row. Another thing with our skid steering suspension is it's actually very common with skid steers to not run suspension. So part of our design is we chose these very large tires. These large tires act as what they call pneumatic suspension. So the tension in not only the rubber, but the air in the tires is acting as suspension, protecting the machine from falling apart, basically. And then if you look at the side profile, you can see each of our components for the drive system. Right here, we have the off-the-shelf Mark 18 porcelain motor. And then we have 2 mounting plates that go on either side. And then these are brought together with 4 square beams. And then obviously on the right, you can see our off-the-shelf tire and wheel. And then there was some interference issues with not only like the mounting plate, but just the rim in general directly to the motor. So we had to design a custom coupler that gives spacing between there, and it can bolt onto both sides. Also, to end out the drive system, another reason that we chose to go with the hydraulic drive system was because of the fact that we knew that we were going to be using hydraulics for the linkage assembly, like lifting and lowering the auger and running the auger. So we thought it was best to make the entire system uniform and just run a hydraulic drive system, since we're already going to be having a motor that has to power the pumps for those two components. So moving on, we have the chassis. So the chassis started off with a simple ladder frame design. So as you can see in the bottom right-hand corner, you have your two main rails that we chose to use C-channels for. The reason that we chose C-channels was for weight reduction and similar strength yields, because if you're comparing C-channels to rectangular tubing, they're very similar in strength, but the weight is significantly lower as it has one less face that it has. So then it's called a simple ladder because it has the two main frame rails, and then it has rungs that go across. Obviously, this design got a lot more complex as time went on, but that's what we started with. And then we have a large reinforced front frame that the linkage assembly goes onto. So from here, you'd have your auger that goes up and down. Then moving on from there, we have the 4 custom motor mounts that our drive system just easily fit into. One of the important features of designing our frame was making sure that everything was not only easy to assemble, but also easy to maintain. So the drive system wheels can easily be inserted and taken out of these simple squares. And then as you go through, you can see each of the different mounting surfaces that we have for all of our different internal components that will be talked about in later slides. And then finally, this crazy looking subframe that's on the outside is our support features for our shell that goes on it. So this is customly designed and fits perfectly to the inside of the shell, and then has mounting points for the shell to attach to.
Seeing as our design is essentially just a tractor without a seat, there are many internal components, just as there are in a tractor. We started with the engine, as Daniel pointed out, a 60 horsepower Perkins 404J E22T diesel engine. So that's a turbo diesel engine. It's shown right here on the right. They also were not available to give us a CAD model. So from the dimensions that were on the specs sheet, we made our own CAD model, and you'll see it in just a minute. We coupled that to a hydraulic pump, shown on the next slide, with the shaft coupling, the flywheel. It's mounted with these Perkins 4.108M engine mounts. And then there's a die-cast aluminum bell housing around that coupling. We routed gas to it from the gas tank with a fuel pump. The Dual-Force closed-loop variable displacement pump was key in our design because our drivetrain is hydraulic, so everything is controlled by this hydraulic system. It's routed from the hydraulic reservoir to the pump, from the pump to a manifold that splits it into 2 different mounting blocks for these 5 directional hydraulic valves. These hydraulic valves are seen right here on the right, have the DO3 mounting pattern, which is just a specific mounting pattern for hydraulic valves. So you have to make sure that your mounting block has the same pattern as your valve. And then you can see just above the mounting pattern that the P pump is always routed to T tank. That's the unenergized valve allows flow from the pump to the tank. So the pump can always be running. We don't have to turn it off. It'll just cycle fluid from the pump to the tank if the valves are not energized. If the valves are energized, you can run fluid from the pump to either A, and then it'll flow back through the component and then into B, and then B will run through the tank. Or if you want to go in reverse, you pump the fluid from P to B, and then it'll run in the reverse direction, come back through A, and then route to the tank. We have 1/2-inch hoses connecting all of the components, and a variety of fittings and plugs. The drive motors are shown right here on the right. There's 4 of them. They're NK18 Auckland motors. We also have 2 radiators to cool the system, and a controls box that includes a battery, a computer, and all of the accelerometer and other fixtures that go along with those. As our project is a little bit complicated already, we did not address those aspects. We just left them alone in the box. And then we also have cable. The internal components, as it's big vehicle, come in at 1,200 pounds. Diesel engine takes up most of that with 533. Hydraulic pump is a 100, and then the full hydraulic reservoir and diesel tanks, both 20 gallons, are approximately 142 pounds each. The control box, including the batteries, 61 pounds, the radiators, 25 pounds, and then we assume that everything else within the assembly is approximately 20 pounds, including the hosing, the fittings, the cables, etc. We did a FEA analysis on our frame. We did it both for the static digging loads and for the driving loads. So for the static digging loads, we fixed the wheel housings, and we placed all the internal components and their weights on their mounting points, and then pushed on the front of the frame as if the auger were pulling down on the frame. That gave a factor of safety of just over 4, and then the driving FEA was we fixed the center line and then put forces equivalent to the weight up on each of the drive motor housings. And that factor of safety was just under 4. And as Daniel pointed out, that is appropriate for what we are intending to build. The center of gravity analysis was also completed. There's an arrow pointing to it here, and it is just behind the front wheels, which is not as far back as we'd like to have it, but it is sufficient to keep the vehicle from toppling forward upon the weight of the auger. Here is a layout of all of our components, where the engine block that we designed from the schematics is in blue, the control box is in green, the hydraulic tank and the diesel fuel tank were both available in the CAD model, and the hydraulic pump is just underneath the hydraulic tank.
So the thermal system, like any, it's honestly really necessary, even in electric vehicles, which don't produce that much heat. They even need to have liquid cooling, because you have to do something with the heat, right? Your material properties will only stay constant under certain temperature ranges. And so given that you don't want the combustion engine to overheat, you need coolant. And then so usually coolant is just a 50-50 water glycol mixture that allows it to stay within a certain temperature band without freezing or vaporizing. And the way it works is that you basically just pass coolant throughout the engine and components that generate heat, and the coolant gets really hot. And then so to dissipate the heat from this coolant, because the heat has to go somewhere, you have the coolant flow through a radiator, which is basically a tank on the top. I'll show you right here. This is a really small tank, well, a small little reservoir, and it has little tubes that allow the liquid to trickle down. And then as the liquid trickles down, there's these aluminum fins that interface with the tubes. And these aluminum fins conduct heat very well. It just heats up the aluminum. And then what you then do is you just suck in air using a fan, and then the cool air will cool down the aluminum fins. And then so to calculate your necessary heat dissipation, well, first you do need to calculate your prescribed heat dissipation, which is a function of your engine design and what RPMs it's going to be running at. And once you know how much heat you need to dissipate, you can calculate a certain surface area you need for the radiator. And you might ask questions like, what about the coolant flow rate? What about the airflow rate? Aren't those also design parameters? And they are, but luckily coolant flow rate is really easy. Once you get above 12 liters per minute, the efficiency just drops off to the point where the marginal returns diminish substantially. So you don't need a standard 12 volt. You don't need that much power. I think you can honestly run it at like a 30 watt pump and then still deliver the 12 liters per minute, given that there's not too much head loss. So basically, yeah, really what you're designing around is the surface area of the radiator. So you calculate the heat dissipation as a function of surface area of the radiator. And then that will give you, once you know your heat dissipation, that will give you the surface area of the radiator. And then so for our design, we had two radiators, one sucking in from the left, one sucking in from the right, dissipates to the top. And yeah, I mean, it also assists in natural convection because heat naturally rises to the top anyway. So basically, to figure out how big your engine needs to be, you have to work backwards. You have to look at how fast you want to go, how much weight you're carrying, and then based off of those design parameters, you figure out how big your engine's going to be. And then so basically, we figured out what our standard acceleration was going to be. We knew what our weight was going to be. And then so based off of efficiency calculations, you can get a ratio of the power to the ground, which is the power of acceleration, to that as a ratio to the power of the engine. So, say you're given like a 60 horsepower engine. If the efficiency of all the intermediate terms, the product of the efficiencies gives you like 50%, then you know that you'll have about 30 horsepower driven to the wheels. And then so we calculate the standard efficiency for a hydraulically driven system. And based off of that, we figured, given this acceleration, we need approximately 60 horsepower. And then something interesting to note is that, for standard internal combustion vehicles, it's actually the case that only 6% of the fuel energy, like the energy that's, in the explosion of octane, actually goes to the motion of your vehicle, which is honestly pretty, it's pretty surprising that it's that low. Your engine's only about 20% thermally efficient. And that's why companies like Toyota have pursued an Atkinson cycle engine so that they can increase that engine efficiency, because that efficiency is really the biggest loss. The engine's 20% efficient, the driveline's like 90% efficient, the wheels are going to be pretty efficient as well. Your main loss is going to be the engine, because if you think about it, an internal combustion engine is just a controlled explosion. And it's really hard to convert all that explosion energy into just mechanical energy. And so that's why your car feels hot after you drive it. And so basically these power calculations allowed us to determine how big our engine needed to be based off of how fast we wanted our vehicle to go. I think another thing that I should touch upon is the design of the drive motors. So a key characteristic of large-scale farm equipment is that it is hydraulically driven. And the reason they do this is because your engine has an ideal RPM range, right? Like your engine doesn't, for diesel engines, you really don't want to go below, I don't remember the exact number, but I want to say like 1200 RPM. That's like, you don't want to go below a certain number for your the piston movement. Otherwise, it's a self-sustained reaction. So if it's not fast enough, then it won't get triggered anymore. And so given that you need a minimum speed, your engine has an ideal RPM range. And because your engine has an ideal RPM range, that means that your wheels will have an ideal RPM range. And then so the way that standard car manufacturers get around this is they have a transmission system that can change the relative speed between the wheels and the piston movements. But this itself has, really substantial limitations. You can only gear something up so much, right? It's standard gearing. You can't gear something this small with something this small with something this big without having a lot of wear. So that's one consideration that we had, and that's why a lot of farm equipment, that goes back to why a lot of farm equipment is hydraulically actuated, because your force amplification on hydraulic systems is much greater because there's not the standard gearing limitations. You don't have to worry about teeth wear. You literally just have to have a differential in the inlet area and the outlet area to achieve your force amplification. And so basically the way our hydraulic motors work is you have like fluid flowing through, and it's kind of like, it's really interesting actually, it's pretty clever. It kind of uses a rotating piston mechanism to drive the wheels and give it a rotational component from an originally a linear pressure, right? So that's what creates that rotational component. You can see that in this GIF right here. And then so the way we've designed our system was that the hydraulic pump was linked to the engine, and then the pump would drive these four hydraulic motors, one on each wheel. And so you would have kind of an inline on the right side and an inline on the left side, but parallel between the left and the right. So it would branch off and then come back into a manifold and then feeding back into the hydraulic reservoir. And Audrey can talk more about how the hydraulic routing works. She has a lot of experience with choosing the engine design and figuring out the specs for that. So I'm gonna let her touch upon that more.
So here's the hydraulic routing system with all the hoses in it. They're in pink and some of them are in gray. It's a little bit convoluted and you can't really tell what's going on down there. So it's much easier to look at this hydraulic routing diagram that we made. The fluid starts in the hydraulic reservoir, goes to the pump. The pump is energized by the diesel engine, and then the pump flows into a two-way manifold. It goes to one of two hydraulic mounting blocks, one with 3 ports, one with 2 ports. Each port of the mounting block has a valve attached to the top of it, and as I mentioned before, it can either run to the tank straight if it's unenergized, or from the pump to A, which is forward, or from the pump to B, which is backwards. So there's 5 components that we're trying to make work really in this system. Those are the left drive, the right drive, the left piston, the right piston, and the auger motor. So each of those has their own routing scheme. Both sides of drive wheels are coupled, so the hydraulic fluid goes in one, to the other in the same direction, and then back to the mounting block. The green arrows signify that the coupling of the component is within the component, so we don't have to do a routing with that. As Peter mentioned, the hosing attachment to a moving part does not function well in SOLIDWORKS. In fact, it makes it crash. So we only have the static parts hosed right now so that we can preserve the functionality of our model. The electrical system is also a key component of our system. Cables come out of the controls box from the battery or the computer or wherever they may be. Individual cables go to each solenoid valve, a positive and a negative, that can be switched because each solenoid valve must be controlled individually. They also come out of the controls box to the fuel pump, to the impact sensor on the front, and to the engine.
Okay, I will be introducing the shell part and the assembly process. We can see that the shell part has been divided into 3 parts: the body shell, front shell, and the drill shell. The body shell has 4 components: front, top, back, left, and right. The body shell is made of HDPE, which stands for high density polyethylene, which is most common use plastic used in pipes. Due to its high density, it will be strong enough for blocking dirt, and the choice of plastic will make it easy to manufacture. There's some small components on the body shell, and they have their functions. The first one is a side panel. We have one on each side, and it's used for accessing the liquid tank to perform repairs and replacement. We have louvers. The big one is one on each side, and the small one is on top. And the top louver is used for ejecting gases from the central components to release heat. And the side ones are used to sucking air to cool the components. The fans are installed to help the process. We have these two black dots on the side. There's two on the left side. It's a filler, and it's used for refueling liquid and fuel tank. The trunk on the back is installed to access the central components for replacement and repairance. We also have the front shell divided in 3 parts, and it's also made by HDPE, and it's functioning as a shell to prevent the dirt coming from the drone. The drill shell is installed for safety consideration, and it's made by 6061 aluminum alloy. And the reason why it's different from the body frame, which is steel, is because only load on it is 3 rubber plates, and they are very light, and aluminum will be enough to hold their weight. And this rubber plate is made from EPDM60 durameter. It's a light and strong rubber enough to block flying rocks. Then it's a blocking process. Then it's an assembly process. We can see that all screws are 0.5 inches at high strength grade A steel cap screws. And the first step is to install all the motors and add tires to the body frame. We have a clear view on the side to show how the process works. Each of the motor has each of the tires individual motors, so the opening process will be fairly easy. The second step is to install the bottom plate and the motor shields. The third step is to install the front shell. If we make it into one part, the gaps has to be made as shown in the graph, which is marked as red. We have to leave this gap for the installment, and this gap can potentially allow some dirt coming from the auger bit to reach the central components, and that will potentially cause some damage. The fourth step is to install the mounts and central components. We can see the frame is specially designed for the mounts, so the installing process can be fairly easy. The components has been introduced earlier in the slides, and I will not go into details about this. The step 5 is to install the, the drilling system and route the hydraulics and electrical connections. There's a closer view which shows how the joints will connect the frame to the linkage system. The sixth step is to install the drill shell and the plates. Please note that the drill shell has to be installed after the drilling system. So if the plates or the frame is broken, it will be easy to repair or replace. The seventh step is to install all the body shell. We have the body shell designed according to the shape of the frame, so we can easily attach them to the frame, and the connection will be stable enough to hold them in their places. The last step is to install all the components on the shell, like the panels, louvers, and trunk, and this process can be fairly easy, and this will finish up the whole process.
So for future work regarding the linkage, one of the main goals that we want to achieve is to reduce the weight of the linkage so that the center of gravity can move back more towards a desirable location. And we can do this in one of 2 ways, or both. One of them is to only use 4 links of the Chebyshev linkage instead of adding the links 5 and 6 that we saw in our design. And then another way we can do it is to only use 1 linkage instead of 2.
For the future work on the chassis, we'd really like to reduce the number of beam profiles. As I was talking about earlier, we chose the primary beam profile of a C-channel for all of the main structural points, but a lot of the internals and stuff like that, I went back and forth on what I was using. So our beam profiles include, square tubing, rectangular tubing, C-channel, angle iron, and having all these different beam profiles makes it difficult for different profiles to line up because the frame has to be welded together and such, and just makes it more difficult in manufacturing. So by reducing the number of beam profiles, it just makes it better for manufacturing and just consistency of design. And then finally, or second, we would like to utilize topology to optimize the chassis design. So as you can see in these two pictures, these are some topologies that we did, and here is like our basic frame design with like where the wheels mount and then the linear actuator mounts, and here like you can see our two frame rails going at a 90 degrees with our 45 support, and the topology actually suggests that we run this kind of funky looking 60 degrees into like another 60 degree bend right here. So add another support beam like that, and then if you're looking at it from the front, you can see that instead of having a square, it's actually suggesting that we run like this trapezoidal shape right here. And finally, one of the important things that we would have liked to done is rearrange our internal components so that we could move the center of gravity further back. So one way we could have done this is by swapping the engine around and putting it in the very back, since the two main high weight features are the engine and then the total linkage assembly that's hanging off the front. And we want the center of gravity to be in between the wheels as best as possible, but right now it's slightly going towards the front, and we've tested that it won't tip, but obviously just for security reasons we'd love to have it as close to the center as we possibly can.
We've been thinking a lot since we finished the project on how we could improve. Those pretty much boil down to 4 things. Setting requirements and objectives for the new project full scale sooner after the project was changed would have helped us a lot. We were spending a lot of time on that, so we bumped back our design process a whole bunch. So we could have done better with that. Stepping up our communication and collaboration. Version control, we had a few incidents where we were working on the same version at the same time and it reverted somebody's work. That was not good. And key is adhering better to self-imposed deadlines. We went over on our Gantt chart a few times, and it again pushed our design further back. Regardless though, we learned a lot about hydraulics, about drive systems. One key thing to point out was that we iterated a whole bunch and found out why tractors look the way that they do. Our end version was version 11, so that tells you how many times we changed it, and we feel like we understand now better why tractors look the way that they do. Thank you.
This meeting is being recorded.